Hi all. Let's see the last topic of fifth unit, branch prediction. In today's lecture, we are going to talk about what is a branch prediction and what are the different types of branch prediction techniques that are used, such as static branch prediction and dynamic branch prediction. So coming to the introduction about branch prediction, in the previous lecture, we have come across one of the design issue of pipelining, which is called as a branch hazards or a control hazards. So in order to overcome the control hazard situation in a pipeline, we come across the different techniques that are used, where some of them are the software based approaches and where some of them are the hardware based approaches. So branch prediction is one of a technique that is used to minimize the penalty which is incurred due to the branch instructions in the pipeline. So let us see in this lecture what is a branch prediction and what are the different types of branch prediction techniques that are possible in a pipeline. So coming to the branch prediction, as we know, it is a technique that is used for reducing the branch penalty, which is caused mainly due to the conditional branch instructions. So because of the penalty or the loss of time which is incurred due to the whenever a conditional branch instruction is encountered in the pipeline, we are in order to overcome this penalty, we implement the concept of branch prediction technique. And these prediction techniques can be used to predict whether the particular branch will be taken or not taken, especially in the case of a conditional branch. Because in case of a unconditional branches, there is no concept of whether the branch will be taken or not taken. At any cost, the branch has to be taken. But in case of a conditional branches, we need to predict whether that particular target instruction of the branch will be executed next in the pipeline or the instruction next to the conditional instruction will be executed has to be executed in the pipeline. So using a prediction technique, we are going to guess or predict whether a branch will be taken or not taken. So we are going to forecast the outcome of a branch instruction before time. So that helps to improve the performance of the system so that your penalty which is incurred due to the conditional branch instructions will be minimized. There are two ways in which a branch can be predicted. One is using a static branch prediction technique and other is using a dynamic branch prediction technique. So let us see each one in detail. The first type of a branch prediction technique is a static branch prediction technique, which is one of the simplest branch prediction technique that is used. This technique does not depend on the information about the history of the branch or history of the code which is executing. And here we are going to predict the outcome of a branch mainly solely based on the branch instruction. And the direction of the prediction, and this particular prediction is done at the runtime of your program. So here you're going to predict the branch in the ID stage of your pipeline, decoding stage of your pipeline. And coming to the static branch prediction technique, it is done either using the concept of compile time heuristic approach or it is implemented using the concept of profiling technique. So static branch prediction using compile time heuristic, it involves making a prediction at the compile time of your program rather than at the runtime of your program. So here it is based on two approaches. The compile time heuristics is based on two approaches. One is based on the predict not taken approach and second one is using a predict taken approach. So let us see how this compile time heuristics technique is used to predict the outcome of a branch. In case of the first technique, the simplest form of a branch predicting technique using the heuristic approach implements the predict not taken approach. In case of predict not taken approach, we are going to predict or ignore the presence of a branch and assume that the branch will not be taken place. And when the branch will not be taken place, we continue to fetch the instructions according to the program order. So after the condition branch instruction, the next instruction we fetch is the actual instruction which is present according to the program order and not the target instruction. So in this method, we are ignoring the presence of a branch and assume that the branch will not take place and continue to fetch the instructions according to the program order. So until the branch is evaluated, the execution of the particular instructions is done in a speculative basis. So here the speculative basis means that the instructions are executed before the processor knows that they are in a correct execution sequence. So even though these particular instructions are being executed, you're not going to update the registers or the memory locations with the results until it is confirmed that the instructions are whatever the order in which the instructions are executed are the same. So after a branch decision is made, the instructions, suppose if there is any error, say that after the actual branch is executed, say the branch is taken, in that case our prediction is wrong. So in those cases, if the branch decision is made and the prediction is based as false, in that case the instructions and associated data which are in the execution units all must be removed from the pipeline, and the correct instructions must be fetched and executed. So until the actual branch decision is made or executed, we'll predict that they're not taken and execute the instructions according to the program order, but we are not going to update the registers or memory locations until it is confirmed that the prediction is correct. If the prediction is correct, the memory locations are updated with the results. If the prediction is wrong, you have to remove the instructions after the conditional branch. Whatever instructions are placed in the pipeline, they have to be removed from the pipeline, and the target instruction has to be fetched and executed. So this type of approach is said to be called as a predict not taken approach. So here we assume that I2 is a branch instruction. So we assume that we predict that the branch is not taken. So we execute the instructions according to the program order, the I3 and I4 instructions, and they are partially executed. So by the time this particular branch instruction is executed, and we here say for example, the target instruction is the next instruction that has to be executed in the pipeline. In that case, it means that our prediction is wrong. We are predicting that not taken, but here prediction is wrong. The branch is taken. So we have to remove these particular instructions which are partially executed, I3 and I4, from the pipeline, and we have to fetch the target instruction and execute it in the pipeline, Fk and Dk. So here this is a timing diagram when the branch decision has been incorrectly predicted as not taken. So the static branch prediction using the heuristic approach, in case of a predict taken approach, we predict that the branch will be taken. So it will always incur a penalty of at least one clock cycle because the target address of the particular branch will be calculated only in the execute stage of the pipeline. So by the time it is being executed, at least one instruction will be fetched and decoded in the pipeline. So if it is a two-stage pipeline, the penalty will be one clock cycle. If it is a four-stage pipeline, the penalty will be two clock cycles. So in case of a predict taken approach, it will always create a penalty of at least one clock cycle while the branch target address is being computed. So if you compare these two approaches of predict taken and predict not taken, in case of a static branch prediction techniques, the predict not taken approach is slightly better compared to a predict taken approach. But when it comes to the complexity, predict taken scheme is more complex to implement compared to a predict not taken scheme. So next comes the static branch prediction technique using the profiling approach. So the predict taken and predict not taken come a static branch prediction technique using compile time heuristics method. Whereas we have other type of a technique called profiling technique, which is involved in the static branch prediction. So the static branch prediction using profiling technique, it is based on the profile information that has been run from the previous runs of the program. So based on the previous runs of the particular program, particular branch, when it is previously run, what is the prediction, whether it is taken or not taken. Based on the profile information of that particular branch, we are going to form a prediction of the branch instruction. So that is called as a profiling technique. Next, coming to a next type of a branch prediction technique, which is a dynamic branch prediction technique. So this dynamic branch prediction technique is mainly used to reduce the branch penalty under a hardware control. As a static branch prediction technique implements the prediction based on the software control, dynamic branch prediction technique reduces the branch penalty under a hardware control using a hardware. So here the direction of each branch is predicted by recording the information in the hardware of your system of the past branch history during the program execution. And here the prediction is done at the runtime In case of static branch prediction, the prediction is done at the compile time of your program. But here during the runtime, dynamically, you're going to predict what is the outcome of a branch. And this branch prediction is done internally in your hardware by collecting the recording the information about the past history of the branch during the execution in the previous runs of your program. So here the prediction is done in the fetch stage of your pipeline. In case of a static branch prediction, it is done in the decode stage of your pipeline. And the simplest dynamic branch prediction scheme is using a branch prediction buffer or a branch history table. So here the branch prediction buffer is nothing but it is a small fast memory which contains the history information about your previous outcome of your branch. So it maintains this particular branch prediction buffer maintains the history information of your outcomes of your branch instruction, previous outcomes of your branch instruction. And that buffer will be helpful to make your prediction at your in case of a dynamic branch prediction technique. So coming to a dynamic branch prediction technique, there are two types of algorithms that are used in a dynamic branch prediction. One is a two-state algorithm and other is a four-state algorithm. So first let us see what is a two-state algorithm. Here we have two states present in our algorithm. One is LNT, other is LT. LNT states that it is likely not to be taken state and LT stands for likely to be taken state. And we have BT and BNT. BT stands for branch taken and BNT stands for branch not taken. Say for example, suppose say that our algorithm starts as LT state, likely to be taken state. So this particular prediction is done based on this particular state of your branch. So likely to be taken states, your condition of your state of your branch is in likely to be taken state. So at this particular state, if you execute that particular branch instruction next time, and next time when this particular branch is executed, it is taken, then the state of your branch will be in the same state of likely to be taken state. And say for example your state of your branch is a likely to be taken state, and when that particular branch is executed next time, it is not taken, the branch is not taken, BNT. So that state of your branch, it moves from LT states to likely not to be taken state. So this particular history will be stored in your branch prediction buffer. So say for example, the state of your branch is a likely not to be taken state. And when next time when that particular branch is executed, and suppose that next time also it is not taken, then it will be in the same state, likely not to be taken. And when the branch is in likely not to be taken state, and when the next time that particular branch instruction is executed, and if it is taken, branch taken, then the state of the particular branch moves from likely not to be taken state to likely to be taken state. So here we have a two-state algorithm which contains two states, likely taken and likely not taken. Requires one bit of the history information for each branch instruction. So here, if it is 0, it means branch not taken. If it is 1, it means branch taken. So you require a 1 bit field which is either 0 or 1. If it is branch is taken, it is 1. Branch is not taken, it is 0. So this particular algorithm, it requires one bit of history information for each branch instruction. Next type of an algorithm is a four-state algorithm which contains four states: strongly not to be taken state, likely not to be taken state, strongly to be taken state, and likely to be taken state. So, and BT and BNT stands for branch taken and branch not taken. So, if you consider this algorithm, say for example, if the state of your branch is a strongly not taken state. So you predict that next time when this particular when this particular branch is executed, it will not be taken. And consider that particular branch is executed. And next time also, when the during the next run of that particular branch instruction, it is again not taken. Then it moves from strongly not taken state to same state. It stays in the same state. So when it is in a strongly not taken state, and next time when the branch is executed and if it is taken, then it moves from strongly not taken state to likely not taken state. So Say for example, if the branch is in likely not taken state, in that case, when the next time it is executed, say it is not taken again. Okay. Next, if it is not taken, it moves from likely not taken state to strongly not taken state. And if it is in a likely not taken state, and when it is executed, if it is branch is taken now, then the state moves from likely not taken state to strongly to be taken state. So this is how it moves from one state to another. So if a branch, it has to move from a strongly not taken state to strongly taken state, it has to move through, it has to prove itself two times. It has to be taken to move from strongly not taken state to strongly to be taken state. Similarly, consider a branch is in a strongly taken state. Next time when it is executed and it is taken again, then it will be in the same state. If it is executed and it is not taken, then it moves from strongly taken state to likely to be taken state. Okay. And when it is in a likely to be taken state, and next time when it is executed and it is taken, it moves from likely to be taken state to strongly to be taken state. Okay. Now consider a situation where the branch is in a likely to be taken state, and say it is executed and it is not taken now. So it moves again from likely to be taken state to strongly not taken state. So if to make a branch move from strongly taken state to strongly not taken state, it should not be taken. B and T, branch not taken, should be proved twice to make a branch prediction move from strongly taken state to strongly not to be taken state. So these states are nothing but the prediction states which are stored in your buffers. So based on this, we are going to predict what might be the outcome of your branch instruction and we'll move forward. And your algorithm works like this. Algorithm will start in LNT state and the branch is executed, and if it is not taken, it moves from LNT state to ST, strongly to be taken state. Else it moves to, if it is not taken, it moves to strongly not taken state. Similarly, suppose the algorithm started is in SNT state, strongly not taken, and if it is executed and if it is taken, then it moves from strongly not taken state to likely not taken state. Or else if it is again not taken, it will be in the same state. And when the branch is in likely not taken state, and when it is executed again, and if it is taken, then it moves from likely not taken to strongly to be taken state. And similarly, the algorithm is in likely to be taken state and the branch is executed and it is taken. It moves from LT to strongly to be taken. If it is not taken, it moves from LT to strongly not taken state. So these are all the different ways in which it moves from one state to another state. So this is a four-state algorithm. This is all about branch prediction. Thank you.